I'll talk in general about quantum communication, but most part of the talk at least those parts which I have specially prepared for students will speak about quantum cryptography specially. So there are different aspects of quantum communication. Quantum communication is not just limited to quantum cryptography. So there are teleportation. It's a very interesting idea that you can send something which is never available in the channel. So it is as if science fiction that I have been sent from here to Delhi, I am disappeared from here and recreated at Delhi. So it's not like fax, because in fax the original remains at the sender's end. It's not like a letter which is available in the channel. It's something special which happens in quantum mechanics only. And most of you know about teleportation, but it has two versions, perfect and probabilistic. So when the channel which I use to teleport is maximally entangled, then we usually get a perfect teleportation, otherwise we get a probabilistic teleportation. Again, teleportation has another version called control teleportation. Usually every communication in quantum mechanics happens between Alice and Bob. So Alice is always the sender, it's always between Alice and Bob. So if there are three parties, then we can have a control teleportation that Alice sends her information to Bob 1 and Bob 2, or Bob and Charlie, and only if Bob and Charlie collaborate, they can reproduce the state which was sent by Alice. Here one has to remember that because of no cloning theorem, one cannot copy a quantum state, so it cannot be sent both to Alice and Bob. So the information must be splitted and reach two people, and that's what is called quantum information splitting. So quantum information splitting and control teleportations are communication protocols which are in some sense equivalent. Then there is quantum secret sharing. So here instead of information I share a secret, and there is other protocol called quantum state sharing. So if you consider the quantum state itself carries your secret, then quantum state sharing is a subset of QSS. I leave it as a problem that control teleportation is some subset of QIS which is equal to QSTS, and that is subset of QSS, quantum secret sharing. Then we come to quantum key distribution. There are two kinds of quantum key distribution, one using discrete variables, one is with continuous variable. So usually all the protocols which we address and which I will review here are discrete variable. There is a continuous variable version as well. We write it as QKD, and so QKD is not the complete cryptographic solution. In QKD we prepare a key and then we use some other protocols to encode a message and send a message. So this will be more clear when I describe one by one protocols. There are two other versions, DSQC and QSDC. They are in some sense better than QKD because you can directly communicate the message through them, and these are also put in one bracket called post cold war cryptography. So here I don't create the key, rather I send the message in a secured manner directly. There is one important aspect of it, all DSQC and QSDC protocol can be reduced to QKD protocol. If I have a random number generator, so instead of sending a meaningful message, if I send a random message, then we will have a random key which will be copied in Bob's end. So to continue, I need to recall some basic aspects of quantum mechanics. In quantum mechanics, for every physical observable, we have an operator. This operator operates on some eigenfunctions, gives you certain eigenvalues. Those are only the possible eigenvalues, and when we expand it in terms of some basis set, we write it at C0, 0 plus C1, 1 plus C2, 2, and I do a measurement, then it collapses into one of the possibilities. This basis set is not unique, so it depends on in which basis I am measuring the state. So when I usually in this literature, when I measure with respect to 0 and 1, we call it computational basis. When we measure it with Hadamard basis, say 1 by root 2 0 plus 1 or 1 by root 2 0 minus 1, we call it a diagonal basis. So this will repeatedly use in the next few slides. Here is something, a basic concept which is very important for us, and it's related to conjugate coding. The question which we want to address, that I want to classify cryptographic protocol. We want to show you that there are only two kind of quantum cryptographic protocol. Although there are several protocols, but they may be reduced to two particular classes. So one of them will depend on conjugate coding, and conjugate coding seems very important. The basic fact behind it is, you cannot distinguish with certainty two non-orthogonal states. So what are non-orthogonal states? If I have xi1 and xi2 and their inner product is non-zero, then I call them non-orthogonal. So if xi1 and xi2 are non-orthogonal, then xi2 can always be decomposed into a non-zero component parallel to xi1. So as if you are thinking this as a state vectors in 2 dimension, if they are not orthogonal, if it is aligned along this direction, it always has a projection along this direction. And when you are saying that the inner product is non-zero, you are essentially saying that its projection is non-zero along that axis. So even if your projector measurement is xi1, you will not be sure whether it is xi1 or xi2. So I just give you an example. Say I have a state alpha 0 plus beta 1 and another state 0. If I do a measurement and get 0, I do not know whether it is alpha 0 plus beta 1 or it is simply 0. So note, corresponding measurement operators do not commute, thus non-conjugate coding is a consequence of non-commutivity. This is a strong statement which I will require for rest of the talk. So these are simple ideas of entanglement which I can skip. Now we come to some cryptographic terms and definition. Cryptography is the art of rendering a message unintelligible to those whom I do not want to send the message, and it is required for everybody from military applications to those who are you are making any communication secure, whether it is your password, whether it is ATM pin. Every time you are using many cryptographic protocols. Cryptanalysis is the art of code breaking, and code breaking is not really a bad thing, because code breakers helped us to develop the civilization and often decided the fate of the civilization. Like in Second World War II, it was the code breaker who decided the fate, because codes of Hitler was broken. And cryptograph systems are cipher, an algorithm which combines the message to be encrypted. So I show you a simple idea of cryptogram. I have a message 0, 1, 0, 0, some sequence of 0 and 1, and there is a key. So if I add up bitwise, then I get a cryptogram. If the other person uses the same key and add up again, he will decode the message. So this is a very simple idea, but it gives you what is message, what is key. So what I need to be required to be secured is key. And in most of the quantum cryptographic protocol, we generate a key in a manner which is unconditionally secured, which does not depend on any assumption, and that makes quantum cryptography better than classical cryptography. So here is a short history of quantum cryptography. In 1970, one paper was written by Wisner which can be considered as the birth of quantum computing, but it was sent to a wrong journal, and it was immediately rejected because of the wrong journals, jargon does not fit. So he published it again in 1983, and in 1984 the first real protocol of QKD appears, which is known as BB84, and one of the B is here. So then comes 91 Eckart protocols, which uses entanglement. BB84 is a 4-state protocol where the bound is known very nicely, and which is a marketable solution is available. And it's interesting to note that during the Soccer World Cup, BB84 was used to practically to keep some information secrets. In 92, Bennett come with another proposals where instead of 4 states, only 2 states are required. It's known as B92 protocol. In 95, Goldenberg and Vedman introduced a protocol which uses orthogonal states. So far these protocols depends on non-orthogonal states and depends on conjugate coding. The orthogonal states protocol is absolutely different, and actually in all non-orthogonal states protocol, some kind of non-realism is required, but in orthogonal state protocol, conjugate coding is not required. You can even have a cryptographic protocol just using non-realism. So this history continues. Then some QSDC protocol appeared in 2002 and 2005. The popular ones are known as ping pong and LM05. So I will describe them quickly. So here is a historical note. It is interesting. There are certain things in quantum mechanics which were really known. Like so many people are now reporting entanglement, that entanglement is seen in this physical system, that physical system. But actually it is difficult to produce a separable system. Separable is much rarer than entangled. If you just look at a quantum system, most of the times you will get entanglement. It's a question whether it is maximally entangled or not. It's a question whether it is useful or not, but most of the times you will get entanglement. Similar is the situation with no cloning. No cloning is the term coined later, and the credit goes to Wouters and Jurek, but actually it was known to many people, and the almost same time Dix found it. So there is a nice statement from Paris. These things were well known to those who know things well. So this is interesting. Many people knew it, and actually in 1970 paper of Wisner it was discussed, and in that paper I just write it in historical note because it's interesting that how the development get delayed. It was sent in 1970 to IEEE transactions on information theory, but it was immediately rejected and it published in 1983 in a SCM journal. There are certain negative ideas of quantum mechanics which people thought that their limitations of quantum mechanics are used to develop quantum cryptography. That's interesting to note. One is wave function collapse or state reduction principle. Whenever I measure a state, it collapses to one of the possibilities depending upon the basis. And this is valid for Eve also. Whenever Eve tries to measure my state, which I am trying to communicate, Eve leaves some traces. And we have clever ways to detect Eve, and that's how we find out whether Eve exists or not. And Eve exists in a channel, I don't use that as key. So this is fundamental. Unitary principle, one cannot simultaneously and accurately measure the value of two non-commuting observables, and there are two consequences of it. If you cannot measure through non-commuting operators, then there is an uncertainty relation related to it, and this uncertainty relations gives you the security in continuous variable quantum cryptography. And this is the reason behind conjugate coding also, that there are two non-orthogonal states basis, you cannot measure a state simultaneously in them. Then there is no cloning theorem, but we will impose a more deeper question. These are the standard ways to look into it. The deeper question is that which of these resources are really quantum? Is no cloning fundamental? Is it a quantum character? Look, superposition comes from linearity. There are possible to construct classical linear theory. If I have a classical linear theory, and what is entanglement? Entanglement is superposition in tensor product space. So classically you can have a tensor product space, classically you can have superposition. So classically you can really have entanglement, but there is some difference. That entanglement is not non-local in character. So classical entanglement is reported in recent past. For construction of no cloning theorem, you just require linearity. Then why don't I see no cloning theorem in classical domain? Why don't I have a classical no cloning theorem? Here comes the fundamental difference. Classically, perfect measurement is allowed. Since perfect measurement is allowed, you can assume that you measure and make a copy. Quantum mechanically, since you cannot make a perfect measurement, then no cloning appears it in true sense. But proof of no cloning require only linearity, and you have many linear classical theories. So these are the, with this perspective, we want to see the quantum cryptographic protocol and view that what actually quantum mechanics use to provide the unconditional security. So we start with a simple-minded idea that Alice prepares a Bell state 00 plus 11, and most of the steps in these protocols are same. I will write 10 protocols, and it will follow that how one can go from one protocol to other protocol. So we just start with a Bell state 00 plus 11. Alice keeps one photon with him and call it home photon, and sends one photon to Bob and call it travel photon. And once Bob says that, well, I have received the photon, one of them measures the photon. So it is simple that since the states are possible at 0, 0 and 1, 1, if Alice gets 0, Bob will also get 0. If Alice gets 1, Bob will also get 1. So they will have a symmetric key. It's pretty simple. So is quantum cryptography that simple? No, there must be something wrong. So what is wrong here? The wrong is that if instead of Bob, Eve appears in between and Eve measures the travel photon, then Eve will also get 0 when Alice's photon collapses to 0. Eve will also get 1 when Alice's photon collapses to 1. And then he can make a copy of this, because 0 and 1 are orthogonal states. You can make copy with a NOT gate, C0 gate, and send it to Bob. And now Bob measures it, and he tells that Alice that, well, I have got this, I have got this. So their results will always be in absolute correlation. They will not be able to detect Eve. So this simple minded protocol, protocol 1 will not work. So I have to look for something better. So what is my strategy? Strategy is that Bob chooses more than one orthogonal basis, non-orthogonal basis. So one may be 0, 1, the computational basis, and the other one may be plus minus. And he chooses it at random. So this now, since Eve does not know which qubit will be measured in which basis, Eve will not know, Eve will leave signature of his measurement. How many times? Say it is sent, Eve measures at randomly using one of the bases. So 50% of the time his basis will match with that of Bob, and once Bob does the measurement, the final outcome will be that 25% of the times result will mismatch, because half of the times when he has even chosen the wrong basis, the result will match. So Eve will leave a trace. So this is the trick, and using this trick I can define a second protocol. And here is an important symmetry. You see that 0 0 plus 1 1 is also plus 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 minus minus. So it keeps the same nature. So if Alice got plus, Bob will also get plus. If Alice got minus, Bob is also expected to get minus. But if there is an Eve in between and Eve has chosen wrong basis, then when they compare their verification string, 1/4 of the time Eve will leave a trace. So what is Eve's strategy? Eve's strategy is not to measure all the qubits, to measure part of the qubit, maybe 10%. But if he measures 10%, he will leave a signature of 2.5%. And what Alice and Bob do? Alice and Bob find out how much error is introduced because of channel noise or because of Eve, and there is a pre-decided threshold. In some protocols, the how much error I can tolerate, that bound is known, but not in all cases. Like in BB84, the bound is known strongly. So if it is above the tolerance limit, then I don't use it as key, and if it is below the tolerance limit, then I use it as key. So it basically generating a key. It is a quantum, these are one-step protocol, one-way, one-step protocol which generates a quantum key, and then you use this quantum key with some classical ideas and make a hybrid protocol of quantum cryptography. Now, in this situation, is it essential to send the entangled state? I started from a very simple idea. I have entangled state, send, measure, get a key. I found that it's wrong. Then I increase one basis. Then I ask a question, is it essential to send entanglement? The answer is no. Because finally it is creating a sequence of 0, 1, plus and minus. So I could have created it, Alice could have created it at Alice's end itself. How? Just by measuring it. If Alice measures these states randomly at 0, 1 basis and plus minus basis, she will get a random string of 0, 1, plus and minus. So entanglement, you don't need to send an entangled particle in the channel. So in the next protocol, we just do this change. So Alice measures it and create it. Rest of the protocol is same. So we are coming closer to a more realistic protocol by stepwise. So in all these protocols, who is giving you security? It is the conjugate coding. It is the fact that Eve cannot simultaneously measure between 0, 1 and plus minus states. You cannot distinguish between a plus state and a 0 state, or a plus state and a 1 state, a minus state and 0 state. This is giving you the security. So who is giving the security? It is the conjugate coding which is providing you the security. We started with entanglement. Now we ask a question that to create a sequence of 0, 1, plus and minus, does Alice require to start from entanglement? The answer is no. Alice can have a random number generator. What is a good random number generator? In quantum mechanics, if you think that you have a state 1 by root 2 0 plus 1 and you measure it, so it's simple that you send a photon, you have a beam splitter, you put a detector here and a detector here. If it is a single photon, either it will come here and or here. If this detector clicks, you call it 0. If this detector clicks, call it 1. So basically, a pure random number generator is a quantum mechanical device where it is understood that it collapses randomly at one of the possible states. And this is what non-realism is. And even if you are using a conjugate coding based protocol, you have to create random number, and you are creating the random number using non-realism. There are protocols which uses only non-realism, which does not require conjugate coding, but you cannot have a protocol which requires conjugate coding only and not non-realism. So So, I can think that a single photon come and randomly Alice choose polarizer either in horizontal vertical or in 45 degree 135 degree. Then it will randomly create a set of sequence of 0, 1, plus and minus. And so, without entanglement I can do it. So, we say that Alice prepares and sends Bob random string of 0, 1, plus and minus, and the rest of the protocol is same. When I do this is a conjugate coding based protocol well known as BB84 protocol, where all the bounds are well known, but we did not follow the usual way to introduce it. We came in a simplified manner. Now, I ask a question. Here it is a 4-state protocol because you are using 0, 1, plus and minus. Do I need 4 states or I can reduce? Because I know that it is difficult for Eve to distinguish between 2 orthogonal states. So, will it work if I start with a random sequence of 0 and plus? The answer is yes, but it is not straight the same way. I cannot say just creating 0 and plus and go ahead. So, that gives you another protocol which is called B92. So, that is also by Charles Bennett in 92. Okay. Before I go to B92, I give a bit of idea. There is an attack called photon number splitting attack. In photon number splitting attack, when a photon is going, it is required to be a single photon in BB84 and such protocols, but we do not have any exact single photon sources. So, what we do? We make probabilistic single photon sources. Sometimes it is giving photon, 1 photon, sometimes it is giving 2, 3, 4. So, what Eve does, Eve uses a beam splitter kind of stuff in which he stops all the pulses where it is single photon, and among the pulses where it is multi photon, he keeps 1 photon and allows all the rest of the photons to go. So, he has 1 copy of each, and later on when Alice and Bob discloses which basis they have used for measurement, he measures with the same basis and find out the state. So, he cannot be detected. Now, you can ask a question that if this is allowed, Alice could have done it. Alice could have used the same attack and stopped all the multi-photon pulses and allow only the single photon pulses. Here is the important conceptual point. Alice is restricted by the present technology, but Eve is not restricted by present technology. Eve is restricted by only the laws of nature, only the laws of quantum mechanics. So, quantum mechanically it is allowed to measure the polarization and number of photons simultaneously, but today I do not have a technology in which I can measure the polarization of photon and number of photon together. The moment I measure the number of photon, I disturb the polarization. So, Eve has an advantage over Alice. Eve is more powerful than Alice. Now, how to avoid this or how to distinguish between the noise and Eve? The idea is you intentionally send some additional multi-photon pulses which are called decoy photon, and Alice knows which pulses are decoy and separately calculate the error rate. Since decoy pulses do not have single photon, they are not stopped mostly by Eve. So, the error rate will be different, but channel is unbiased. So, we can distinguish between the channel and Eve. Decoy is a very nice idea. So far we have seen that entanglement is not required, but we need 4 states. Now, we come to a B92 which is a 2-state protocol. So, our state in 0 and plus is same, 0 means 0 and plus means 1. Now, you see if a simple minded idea would have been that if Bob also measures and check that they are getting the same thing or not, but it is done in other way. If Bob gets 0, he cannot know whether it is 0 or plus, but if Bob gets 1, then Bob definitely knows it was plus. If Bob get 1, he knows it is plus, and if say in other way around, if Bob get minus, so minus was not sent by Alice, so if there is no if, then it must be, the initial state must be 0. So, what do they? Bob keeps all cases where his measurement outcome is 1 or minus, not the 0 and plus. So, that is interesting. And discard all other cases. Bob neither announces the basis used to make a particular measurement nor the outcome. He just announces which qubits are to be kept and which are to be discarded. Following Bob's announcement, Alice discard all such qubits and they just get a symmetric key because they know the encoding, that what plus means and what minus means. So, this is B92, which is a two-state protocol. So far all the protocols which we have used is a conjugate coding based protocol. Security of protocol 2 and 5 are ensured by conjugate coding, but non-realism is required for generation of random numbers. These are requirement for the classification scheme which I want to introduce. Entanglement is not essential. All these protocols are used to distribute secured key by quantum means. So, they are called QKD. All these protocols are one way and one step. I told this specifically because next I will create two-step protocols and two-way protocols. Questions that arise in our mind: can we design a protocol for secure direct communication using quantum means? Can we design, so I want to go beyond just generating a key. I want to send the message directly. Can we design one-way two-step protocol? The answer to all these questions are yes. So, we will start. Let us some more complexity to the simple-minded protocol and make it two-way. This protocol has a nice name, it is called ping pong. So, it is like a ping pong ball, a qubit goes and come back. So, it starts with the same idea that Alice and Bob, so since all the messages have to be sent by Alice, now Bob creates the entanglement. Bob creates the entanglement, keep one photon with himself and send a photon to Alice. So, what Alice does, if Alice has to send a message bit 0, then Alice does nothing, just return it back. If Alice has to send a message bit 1, then Alice apply a NOT gate and send it back. So, if the initial state was say 0 0 plus 1 1, then if Alice has sent 0, then Bob will receive back 0 0 plus 1 1. If Alice has sent not encoding 1, then second 0 will become 1. So, it will become 0 1 plus 1 0. Now, orthogonal states can be distinguished and the Bell states are orthogonal states. So, a Bell measurement can be done by Bob and Bob knows which encoding was done, but what will give the security? So, part of the string sent by them are measured with non-orthogonal basis like 0 0 and plus minus, and that verifies whether if exists or not. So, this is the traditional ping pong. I will introduce, we have a version of ping pong which does not require this conjugate coding. I will come to that in end. So, this is the idea behind ping pong. Now, I ask a question. So, what changes? Earlier it was only QKD, now I have a direct message sending protocol, one thing. Can I use it for quantum key distribution? Answer is yes. Instead of sending a meaningful message, if Alice uses a random number generator, measures and get a random string, and whatever he gets in random string, he sends that to Bob, then it will be a key. So, you can use all this kind of QSDC protocol to generate a key. The question is entanglement required? The answer is no. There is another version which is called LM05, Lukamini Masini, which was introduced in 2005. So, it starts with the same kind of idea, a string of 0, 1, plus and minus, and the encoding is done in this way. And so, after the encoding, the state which is written must be distinguishable from the input state, which is the case, and since Bob knows which state he had prepared, he will measure with the same basis and Bob will always get. But again, this is a conjugate coding based protocol. Now, so far we have seen that it is two-way. Can we make it one way? The answer is again yes, we can make it one way. So, first I tell you that ping pong and LM05 are QSDC protocol. There were two things I have written in the beginning, one is QSDC and one is DSQC. QSDC stands for Quantum Secure Direct Communication. DSQC is used for Deterministic Secure Quantum Communication. So, what is the difference? They are doing the same thing. In QSDC, I do not read any additional classical communication. In DSQC, which is required. So far in LM05 and ping pong, I have not used any classical communication to decode the message. We have done some classical communication to detect if, so that is not counted. So, this is QSDC, both LM05 and ping pong are called QSDC. So, next we come to a one-way protocol, and I am introducing it in such a way that everything appears similar. So, in this one-way protocol, Alice prepares n copies of Bell state. She keeps the first qubit of all entangled pairs with her and sends the second qubit to Bob. This is a typos. Now, Alice randomly chooses a set of qubits from the string and forms a verification string. and the verification protocol is same, you use the conjugate coding. So, the idea is he divides the superposition into two parts. I told you again, the entanglement is nothing but superposition in tensor product space. So, superposition is divided into two parts. One particle is sent in the beginning, at the same time the other particle is not available in the channel. If both are available in the channel at the same time, then you can do Bell measurement and find out what is sent. So, what he does, he sends one particle first, so he creates, you can think that he creates a sequence with all the first particle and a sequence with all the second particle. He sends the first particle, set of first particle first, ensures that Bob has receipts, and after Bob has receipts, he uses part of it as verification string and find out whether Eve exists or not by following BB84 kind of check. Then in the remaining qubits, he keeps some for verification, and on rest he applies dense coding kind of operation. Say he applies sigma x to encode 1, identity to encode 0, 0 0, sigma x to 1, 1 0 1, I sigma y to 1 0, sigma z to. These are Pauli matrices, you can write it as x y z or sigma x, sigma y, sigma z, and they are all one qubit gate. And in dense coding, you know that they map one Bell state into another uniquely. So, if it is done and send it to Bob, Bob knows what was the initial state, and now Bob measures the final state by Bell measurement, then Bob knows what information has been sent. So, here is a point, you see that this could have been done in ping pong protocol itself, but the idea of Bostrom-Felblinger was not to show the efficiency is more, rather their idea was to show that direct communication is possible. So, they did not try, it is a simple extension of ping pong protocol. So, it can be made one way, but in one way, since we have to ensure that the entire superposition is not available at the same time in the channel to avoid eavesdropping, it has become two step. So, can I make it one step? Yes, there is a trick again for that. To do it one step, which I described as the next protocol, but it is what we do, we create a sequence of P of the first particle, I create a sequence of all the second particle, and then I change the order of the second particle. Alice changes the order of the second particle. First he sends the entire sequence of the first particles, and then he does the encoding by using dense coding, then he makes rearrangement of the order of particle and send it to Bob. They detect Eve by BB84 kind of check. This has become one step, one way. Even if Eve is there in the channel and Eve get access to both the photon, but he does not know which photon of sequence 1 is entangled with which photon of the sequence 2. The first photon of sequence 1 is entangled with third photon or fifth photon, so he does not get any information. So, rearrangement of order of particles is an excellent trick. It can reduce two-step protocol into one-step protocol, but now Alice has to disclose which is the sequence. So, for encoding you require some classical information. So, this has reduced from QSDC to DSQC. So, this is how we go from one set of protocol to another set of protocol. I have a set of theorem to show that which protocol is reducible to which in terms of security proof. So, here this is the protocol where we use this sequence changing rearrangement of order particles, and instead of Bell states I use a GHG like state. So, the states are something like this, but this is just to show that these states can also work, and this is a paper of mine with Anindita, but the idea is that initially many papers were written in this line, that somebody had shown that it can be done with GHG like state, somebody had shown that it can be done in GHG states, but it can actually be done in any systems where dense coding is possible. So, there is no meaning in writing thousands of papers in the same field. Any systems where dense coding is possible, you can design an efficient protocol for DSQC. So, you can use partially the power of dense coding or full, but we have some observations, we will come to that. So, this is the table, means what if your input is known, what is the output and decoded secret. So, the observation is that efficiency of a protocol is defined as C divided by C plus Q, where the C is the amount of classical bits, amount of information, classical information sent in terms of bit, and Q is the number of Q bits used. So, initially what people are doing, why the efficiency of these protocols were less, was on the fact that no encoding was done on the travel photon. Encoding was always done in home photon. So, if you have a 4 qubit W state, you can use 2 for encoding and 2 as only as travel photon, but you do not need that. You can do the encoding in travel photon as well. You do not need to do the encoding in home photon. So, first we find that when in GHG like state, I do the encoding in 2 photons and keep one as home photon and send rest 2 as travel photon, then efficiency increases. So, this was our first realization. Then we find out that we do not need to do that. We can use dense coding, rearrangement of order of particles, and if I do not count the decoy photons, then the efficiency will be 100%, but you have to count decoy photons, but efficiency is more. Then comes a situation that can it be improved further? Can I improve the efficiency of DSQC further? There is a possibility that I use hyperentanglement. So, hyperentanglement is entanglement in the same particle in different degrees of freedom. So, in terms of qubit, the efficiency will not increase. So, suppose you are sending the same photon, but now it carries 2 qubit of information. So, you are sending the equal amount of qubit. So, if you try to calculate efficiency of hyperentanglement based DSQC, it does not improve. So, we modify this definition and we introduce a new concept of efficiency where Q is the number of particles used to carry the qubits. So, we actually count number of photons, and so you can call it a physical efficiency, and physical efficiency will only increase when we use hyperentanglement. And there are nice ways to now distinguish between hyperentangled states. So, hyperentanglement, so the simple idea is that whenever there is a dense coding, you have a set of quantum states, basis, you know the operations through which dense coding is possible. There is a one-to-one mapping between dense coding and DSQC. There is already few papers on dense coding and teleportation one-to-one map. So, you can map teleportation and DSQC schemes based on rearrangement of order particles. They have a one-to-one map. So, this is one of our recent observations, but this is not that exciting. We wanted to speak on a more exciting observations on classification of cryptographic protocols, but that required to introduce a protocol which is very important and which you can consider a benchmark in a class in itself. As important BB84 is in general for all the protocols I have described so far, Weidman and Goldenberg protocol is that important. So far some way or other we have used that non-orthogonal states cannot be distinguished. So, it was a belief that for quantum cryptography you will require non-orthogonal states, but Weidman-Goldenberg protocol shows that you can even do with orthogonal states. So, what is done? You have 2 wave packets, localized wave packets A and B, and they are in superposition, one by square root A plus B and one by square root A minus B. We send it through a channel, but we send it in such a way that both A and B are not available at the same time in the channel. So, it is a Mach-Zehnder interferometer, you can easily identify it. So, here is a delay. So, one part is delayed in the Alice's end and one part is delayed in the Bob's end. So, they superpose properly here. So, what is important? That delay must be same in both sides. What else is important? Now, the checking should be different. Now, I have to check the time. I know the time when Alice has sent the photon. I know the time it is delayed. So, time of sending plus delay time plus communication time must give me the time when Bob receives the photon. So, if that matches, that means Eve is not at least delaying the photon. Okay? So, that is one check. Second check is that, and unless if delay the photon, Eve cannot get the information, because A itself does not carry any information, B itself does not carry any information. The information is encoded in the relative phase between them, and unless you have the entire superposition, you do not get that information. So, superposition is divided into 2 parts. Now, the tests are, if TR is the receiver's, so TS is sender's time, this is the delay time, and tau is the delay time and theta is the travelling time. So, added up time will be same, and then they can use a verification string to check all the strings they have got are same or not. So, this is a nice protocol which uses orthogonal states, which is completely secured, and it does not depend on conjugate coding. It uses only non-realism. Now, can I use this to form a DSQC protocol? Can I use it to form ping pong kind of protocol? The answer is yes. These are our recent finding, and we find it that assume that it is straight to explain, but it was very difficult to locate the symmetry. So, now we come to the symmetry of this protocol. Assume that in the above protocol, Bob sends a random string of J0 and J1. So, J0 and J1 is as described here to Alice, and Alice encodes 0 or 1 just by applying identity or fetch flip operation. So, here is only one operation applicable, because you have to distinguish between J0 and J1, and the difference is in fetch. You have two states. So, fetch flip operations and returns the state by using same protocol. Bob will measure the final state, and since he knows the initial states, he will be able to decode the Alice's message. So, it is the same as ping pong. Eve may learn the final state, but since he does not know the initial state, how does we know that he does not know initial state? Because when it was sending, before encoding, I have already checked by Wedman-Goldmer whether eavesdropping is happening or not. So, since I already know that eavesdropping is not happening, Eve does not know the initial state. Since Eve does not know initial state, even if he came to know about the final state, Eve will not get the encoded information. So, this is a only superposition based version of ping pong. Above tests implied to protocol 8 and 9, which is depend on rearrangement protocols and Deng protocols, and make them free of conjugate coding. Thus, we can do all these tasks by using non-realism only. Now, we are ready to, I have described more or less all the discrete variable protocols, and we are ready to classify them. And I ask a more deeper questions. Which quantum resources are used for quantum communications, which are really quantum? There can be a broad classification that these are uses 2-state protocol, these are 4-state, these are 6 states, but they are artifact. There can be like they use entanglement, they don't use entanglement, they use Bell measurement, they don't use Bell measurement. But more deeper is whether it uses only superposition or whether it uses conjugate coding. So, our observation is that it may not only lead to classify cryptographic protocol, it may lead to rebuild the assumptions of quantum mechanics as well. So, next two slides contain most part of the present lectures in terms of observations. So, no cloning principle, which I was telling that it requires only linearity to prove the no cloning theorem. Therefore, we will say it in classical waves too, but linear theories of classical domain does not provide any no cloning theorem. Why? Because perfect measurement is allowed. So, no cloning is not really quantum mechanical. What makes it quantum mechanical is non-availability of perfect measurement or non-realism. So, who plays the crucial role in providing the security? It is non-realism. Then we come to entanglement. It is superposition in tensor product space. So, classical tensor product space exists, and that along with linearity, a linear theory can give you classical entanglement. Simon has a nice report on it. Non-local nature makes quantum entanglement special. What gives non-locality? Non-realism and no signaling imposes non-local character of a linear theory in tensor product space. As no signaling also happens in classical world, so most crucial component is non-realism. Here I also want to make a point. There is some ideas on non-local boxes which we are looking very deeply, or they are often called PR boxes. In PR boxes claim that they don't need to refer to anything else, and they can construct quantum cryptographic protocol. It is not surprising, it is not unexpected. Why? Because non-realism is already inbuilt in non-locality. If non-realism is there, and we have shown that non-realism alone is sufficient to design quantum cryptographic protocol. So, even if you design quantum cryptographic protocol with PR boxes, that is expected to reduce to the non-realism based protocol. Then it comes to interesting idea, a local variable. A local variable can be influenced only by events in its backward light cone and not by events outside, and can influence events in its forward light cone only. So, this is a strong statement of causality, and there is a nice point that most of the quantum mechanics which I do we call it non-relativistic. But in non-relativistic quantum mechanics, when I use this notion of locality and non-locality, I use actually relativity inside it, kind of relativity. So this is interesting to note for the students that somewhere relativity is embedded in your standard quantum mechanics when you define local variable. So quantum mechanics is real black magic calculus. Okay. Then I come to a point, non-commutativity. Non-commutativity is a very important quantum resource. Yields conjugate coding, it is an important resource for many QKD and QSDC protocols, and we have seen that non-realism is sufficient to derive protocols for quantum cryptography. This also gives you uncertainty relation. These things, conjugate coding, non-commutativity, uncertainty relation, these all are connected. You know that in quantum mechanics for every observable you have operator. For measurement you can write operator. If the operators do not commute, for non-orthogonal states the operators do not commute, so you cannot measure them simultaneously with certainty. Same is the statement of uncertainty. If they do not commute, there is uncertainty relation between them, you cannot measure them simultaneously with arbitrary accuracy. So they are closely linked, but there are some protocols on continuous variable cryptography which depend solely on uncertainty principle. So they, a more strong statement is all these protocols belong to one class, they belong, their quantumness comes from non-commutativity or non-realism. So non-realism is fundamental. The other set of protocols, so what is non-realism? The assumption that quantum measurements yields probabilistic outcomes in accordance to Born rule. So this is the main assumptions which gives you unconditional security in quantum cryptography. Then we find that non-realism in particular and quantum measurement postulates in general provides us the essential features of quantum communication. Second most important quantum resource is non-commutativity, and we classify quantum cryptographic protocols in two parts. One depends on non-realism only, and the other one depends on non-realism and non-commutativity. So depending upon which of the above is used, we often unconditional security. Now I will quickly introduce few other communications problems which we do, and we will not be able to justice with them because of timing, but I will just tell about them. So one problem which I do is, which we have done recently, is called quantum cryptographic switch. The idea is we want to devise a quantum switch which is a third party Charlie can control to a continuously varying degree the amount of information the receiver Bob receives after a semi-honest sender Alice has sent her information. So I define the problem in this way. There is a company in which Charlie, Alice, Bob all are employed. Charlie is director of the company and Alice is a custodian of all the files. So in university system you can assume that Charlie is vice chancellor and Alice is registrar and Bob is another employee. So registers want to send some information to him. So VC, but it is subject to VC's permission, and when he permits, but he tells that Bob will not be able to read it till I permit. And when he permits, he can give, Bob will require some information from Charlie and he can control it to various degree that how much information will be obtained by Bob. So this is the idea behind switch, and there are many analogous problems. There may be a military battlefield and a map is with the archive person and the general gives a soldier the permission to fire, but the map, but when to use the map, that control is with the general. You can assume a situation like when you have some stocks in market, you want to sell them, so you give the passwords and things to your broker, but you did not allow him to sell without your permission, so you keep some control in your hand. So cryptographic switch is a very practical thing. So here also the protocol goes almost in the same way. Alice wants to send it to Bob, so Alice requires Charlie that can I send it to Bob. Then Charlie makes some set of entangled photons, a Bell states, and creates one sequence with all the first photons, send it to Alice, another sequence with all the second photon, send it to Bob, but before sending it to Bob, he changes the order of the sequence in which he is sending it to Bob. So even if Alice and Bob collaborate among themselves, they do not know which particle is entangled with which particle in the other sequence, so they will not be able to know the state of the sent by Charlie. Now what Alice does, receiving this photon, Alice has to send a set of A file means a set of bits, classical bits. So he does dense coding. So once he does dense coding or hyper dense coding and sends his photon to Bob. Now we have to do one assumption in all this kind of tripartite protocol, that Alice has to be semi-honest. If Alice is not semi-honest, then these protocols will not work. So semi-honest means Alice respects the protocol, but remaining within the protocol, Alice can try to avoid Charlie's control. So this rearrangement business avoids that. Now once Bob receives all these photons, then Bob requires Charlie's input. Charlie has to tell what was the right sequence and which photon, which Bell state he had prepared. Then only Bob will be able to decode the information. So Bob needs 2 bits of classical information that we call key information C, and C can be varied to a continuous degree from 0 to 2, and with the variation of C, the information obtained by Bob will vary, and that is the notion of switch here. So with respect to Bob, he will receive an ensemble of Bell states. He will not receive the Bell state directly because he does not know which Bell state has come to him. And then in ensembles we use usual tricks that projection operators applied. We calculate Hollebo bound, Hollebo quantity, and C is the amount of Charlie's essential information, and we parameterize the amount of key information Charlie reveals by means of a single variable theta, and we write it like this and define A and B as this. So these are standard ways to do, and this is the how the Hollebo quantity varies with C. Then we can consider a noisy case in which we consider the action of a squeezed generalized amplitude damping channel, and it is written by standard Krauss operators, and this are the noisy situations. This is Hollebo quantity, this is a squeezing parameter R, and this is the classical information C, key information. So this is the bit short idea of switch which we have done very recently, and maybe in this month only we put it in archive. There is, so communication is not limited to cryptography. That is what I told in the beginning before I introduced the scheme for classification of cryptography. We do something else also. We have a protocol for Bell state discrimination. It is a paper in IHQI, and we try to distinguish between this kind of states, generalized Bell state x plus x bar. So for n is equal to 2, this is a Bell state, n is equal to 3, it is a GHG state, it is general exact state. So it is known that you need at least 2 copies for 4 orthogonal Bell states to distinguish them, but we do not want to put the restriction of LOCC. We wanted to check that whether we can distinguish them if we work beyond LOCC, if I am allowed for non-local operations, and the answer is yes. So this is one of the circuits. So this circuits, you see, this ancilla goes all around, and this has access to 2 variables which are not local, and we do the measurement on ancilla, so the main entangled state is not destroyed, and comparing these results you can find out which Bell state it is. So now this is a special case when you can distinguish Bell states, and it is easy to see that one of them will give the parity, the other one will give fetch. So looking at the measurement, I can identify that it is J plus J minus phi plus phi minus. But this is a concept in itself that you can outsource some of the measurement, and again here you use non-commutativity. The measurements which commute can be simultaneously outsourced to ancilla, and we have a set of theorem. Given a unitary operator U and an observable W, compatible with it means its conjugate W comma U is equal to 0. It commutes. Measurements of W can be outsourced to an ancilla using control operations. So this theorem helps us to do something very relevant to communications. There are some corollary, and these are another theorem which makes these 2 circuits equivalent. So this is what we want to come. So if we use an ancilla which propagates and non-local communication is allowed, and then there are 2 ways to communicate. You have a network of quantum resources, and there are two ways to communicate using this entangled states. One is that you measure and recreate and send, and one is use the ancilla to pass through all of them. So it will depend on the topology which one is relevant. So in our case, the topology of the network is important. Our strategy is costlier in star topology. If you can think of a quantum internet, here is a network, here is a network, and here is a long haul connections, then our strategy is exponentially cheaper. These are the situations when our strategy is quadratically better than measurement and recent kind of thing. So another thing means, in the beginning I told that there are many different aspects of quantum communications which we deal. One is quantum teleportation, and quantum teleportation is well known so far, but we have seen that means if you know that there are only certain possibilities and you want to teleport one of them, then life is easier. You don't need much resources. You can send even a large state with a small quantum channel. So one such example is, this is usual teleportation, that you have an unknown state which is x plus x bar kind, and you have a channel which is a Bell state. Instead of alpha beta, I would like to put 1 by root 2, and you can communicate the entire channel just by sending some additional classical bits. So you can teleport a n qubit states, but provided they have an intrinsic symmetry, they have a symmetry that they are Bell type of states. So these are the derivations which I am averting. This is in our this year's IGQI paper which I refer. So these are most of the references, and I summarize that we start with the basic idea behind quantum cryptographic protocol. I reviewed most of the protocol and find that there is an intrinsic symmetry. You can state with a simple-minded protocol that you have a Bell state, one particle is kept, other particle is sent, other particle is measured, but this will generate a symmetric key and which word. So this I'll stop. Thank you for listening me.